Hello, it's Keith here, and this is lesson 2 of my 68,000 assembly programming tutorials. Now, we looked last time at how to do basic mathematics, moving of data into registers, but now we need to go a little bit further. It's important we understand the addressing modes that are available to us on the 68,000 processor, because in a lot of cases we have some quite powerful options for where to get the data for our commands, or where our commands should store the result to. So let's have a look now at all of the different addressing modes, and we'll see some examples of them in action. Now, for today's example, we are going to need to do some preparation. So what we're going to do is we're going to load some test data into some spare memory. The test data is here, and the memory address we will be storing to is this one here. And we do have a memdump command, which we're going to use to dump that memory to screen so we can see the results of that preparation. Then we're going to clear the D0 register. We're going to set A1 to point to the middle of the memory that we've just set up, and we're going to set D1 to a 1. And this is going to be our test data for all of the examples we're going to do today. Now, one very important thing I need to point out is this thing of writing to fixed locations within the memory will not work on most 68,000 systems. I wouldn't usually do this, I just want some very simple examples, and for that reason we're going to be running only on the Genesis system today, because that memory location is fixed for the Genesis's RAM. Now, although we're only running on the Genesis, the concepts we're looking at today, the addressing modes, are completely valid on every system. So don't think that the fact that we're only doing it on the Genesis means this is not relevant to anything except the Genesis. It's completely relevant to all 68,000 processors. The commands we're going to be looking at today are available on every 68,000 system. Some of the more advanced commands would be on the 68,010, etc. But we're not looking at those kind of commands in these tutorials. These commands can work on every 68,000 system. So you can see here a sample execution of the program without doing any commands. And so we're setting this memory area here to these 32 bytes. And these will be our test data for all of today's examples. So we're going to go through each one of the commands one by one. Now, one thing I'd like to point out to you is I have a cheat sheet available on my website. I'd strongly recommend you download it because it's what I use for all of my programming. And if you do so, it should help you when you're learning 68,000. It's a good thing to look up and to check what commands exist and what the options are. You can see here that it shows which commands can work at the byte, word and long level. And what I'd like to point you to today is you'll see quite often this EA command here. Now, this stands for effective address, and whenever you see this, you have various options for the source or destination of your command, and it's going to be those that we're going to be looking at today. I should, however, say it's not the case that all the addressing options are available for all commands. There are some permutations and combinations that don't work, but generally speaking, the majority of cases they will all be available. Anyway, let's have a look at each of the addressing methods, and I think it'll start to become clearer what they are and why they are so powerful and why they make the 68,000 such an impressive processor. So the first one is the most simple, and we actually saw this last time. It's called immediate addressing. This is simply where the parameter that we're using is specified with the command, and we saw this before when we were using a hash symbol to mark a number that we were storing into a register. So here's a very simple example here, and the immediate value is here with this hash at the start as usual, and we're moving it into the D0 register, and we're moving a long word here of 32 bits. And if we execute this now, we will see the result. So our RAM didn't make any difference in this case. We've just loaded 1 to 8 as a hexadecimal number into D0. So that was our immediate value. So that was immediate addressing, very simple. I don't think that's probably too challenging for anyone. Well, let's have a look at the next one. So next we're going to be looking at absolute addressing. Now, absolute addressing is where we're reading from memory, and we did also cover this last time. So if we don't specify a hash, we can specify a $1 for hexadecimal, but either way, a number without a hash will be a memory address, and it will read directly from that memory address. So in this case, we're going to load from FF0100. And if you look at my example code here, we are loading from the middle of the example data that I loaded into memory. There is a very important thing that we need to look at this point, and that is the order that the bytes were loaded in. Now, we loaded in a word, and a word is 2 bytes. And the first byte in our memory was loaded into the most significant byte of the word in RAM here. And the second byte was loaded into the least significant. Now, if you're not familiar with programming of assembly machines before, that probably seems quite logical to you. But surprisingly, it's actually the opposite of basically what every other machine in existence does, really. The Z80 is known as little endian. It would have loaded them backwards. The F0 would have been the least significant byte and the F1 would have been the most significant. That's also true of the 6502. It's true in almost all cases of the ARM processor. It's true of the x86, the 386 and so on. It's basically true of every other processor except the 68000. The 68000 is known as big endian because the first end is the big value. Apparently that's really where it comes from, the name. I can just give you another example of this. If we change this to move L, you'll now see that the far left is F0 and so on. F1, F2, F3 makes up the values. As I say, if this was a little endian system, you would have seen F3, F2, F1, F0 here. But that's just something important that you do need to understand. If you've never programmed the other systems before, you're probably not going to worry about that, and it might even be better for you. But if you're used to programming Z80 or 6502, that's probably going to surprise you quite a bit, and maybe you're going to make some mistakes with it. So it's important for you to know. But anyway, absolute memory addressing just gives a full address, and we read straight from that address.
Now, one important thing about the 68000 processor is with regards to the word and the long commands when we're doing addressing. Now, I can do a command like this and it will work just fine. You can see we can get our monitor result. But if I try to read a long or a word from an odd valued address, you see I'm getting a crash here. There's no monitor showing. Now, unfortunately, the example I showed last week was actually doing that correctly, and the reason it was working was because the Genesis emulator I'm using is actually overlooking that limitation of the 68000 processor, and I have to thank Howard Jones, who commented on my YouTube channel correcting me on that. But you can only read from even boundaries with words or longs with regards to memory addressing, and that's true of absolute addressing in this case, or addressing that uses an A register as well. So that's something important to know about the limitations of the 68000 processor with L's and W's. You can, of course, do bytes just fine in this mode though. So bytes will read fine from odd addresses, but words and longs can only be loaded from even addresses.
So that's very straightforward. So as we just saw, the bytes will be loaded in from the consecutive bytes after the starting address that we specified. Now, another very straightforward addressing mode is what's known as data register direct addressing. It sounds overly complex. What it means is copying one data register to another. Of course, data registers start with a D, and so all we're doing is we're copying one data register to another. So you can see here we've just copied D1 to D0. Very easy there. Another equally simple one, but it does have a different name, is address register direct addressing. This is exactly the same thing, only we're using an address register rather than a data register. In this case, we're copying an address register to a data register, and then we're running the monitor. And you can see here, we've copied the address register 1 here into data register 0. Very straightforward. Of course, address registers have fewer mathematical options available to them, but in this case, we can copy address registers to data registers and vice versa. So that's again all that is. Very simple indeed. Much more useful is address register indirect addressing. This is where we store an address inside of an address register, and then we read in the value that's contained in the address in that address register. Sounds a little bit confusing maybe, but it's pretty straightforward when we look at it. So if we imagine that our address register contains FF0100, which it does in our example, then what we will do is we will load in from that address the byte, word or long from the bytes from that address that we've specified in A1. So effectively we're reading in from the same address as we did up here with absolute addressing, but we're doing it indirectly via the A1 register because A1 now equals that value here. So let's try that out. So all we needed to do is specify the brackets here, and that told it to load the address from the address in A1 rather than loading the value of A1. And you can see that has worked here, F0F1, which is of course the address FF0100, the 2 bytes afterwards because we loaded in a word here. So very good. Now this is where things get quite curious, and this is something that really surprised me about the 68000 processor. We're going to look at an addressing mode called address register indirect with post-increment. What this does, it's almost the same as the last method where we load in from the address held in an address register, but immediately afterwards we increment the address register. And we actually increment the address register not by just one, but actually by the amount that we read. So in the case of reading a word, the address register would have 2 added. But if we'd just read in a byte, it would have only been incremented by 1. And if we'd have read in a long word, we would have incremented it by 4. So whatever the address register starts as will be changed by the amount that we read in. And of course, the value we read in will be read in exactly the same as in the previous example. Well, what's the point of this? Well, for one thing, if you're reading in bytes to show to the screen or to save to another location, we don't need to change the address register that we're using to read in those locations. But even more surprisingly than that is the 68000 doesn't have a dedicated push and pop command, which is used in Z80 and 6502 for backing up and restoring registers. This is actually our push and pop command. It's completely as efficient as push and pop, and it actually has the benefit that we can use every single one of our address registers as a stack pointer. Now, I know I've not covered stack pointers yet. We are going to cover them in a later lesson. I just wanted to mention that at this point that if you're wondering where your push pop commands are, this is your push pop command. This is what we use to do it. So effectively, every time we read in, we're updating that address register, and it's moving further backward in the address range if you think of it as a stack. And so this is how we can use it to do stacks, but we can also use it for consecutive reading, as in LDI on the Z80. So very, very powerful option here. So let's see that in action then. So you can see here that A1 has changed and it's gone up by 2, and we've read in the 2 bytes here. Well, let's try some other options here. Well, what if we change this to a B and run it again? Well, you can see now it's only gone up by 1. So, and we've only read in 1 byte, of course. So the address register is changed to point to the next byte after the one we read in. Of course, if we change this to long word, we're now reading in 4 bytes. So you can see the address register has gone up by 4, and we've loaded in 4 bytes here. And we would now read in this if we continued doing that. We could, of course, do this. Why not? I'll just show you that. So you can see here, we've now loaded in another 4 bytes in the same way. So this post increment allows us to read in very, very quickly. And obviously we could put this in a loop, and we could even have a destination. It's perfectly valid to do A2 plus as well. I mean, it won't do anything particularly pleasant in this case because we've not configured for that, but it will work just fine. One thing you can't do is you can't do a post decrement. There is no such command. Post increment is all you have. So that's something important to notice.
Now, I said before that the 68000 can only load longs and words from even addresses, and that has a quite interesting effect on the stack pointer, the A7 register, when it comes to reading and writing bytes. Now, you see, the stack pointer always needs to be ready to read a word or a long, or write one, of course, and the 68000 can only do that on even addresses. So rather strangely, if we write a single byte to the A7 or stack pointer register, which are the same thing, then it will actually move by 2 bytes, whereas if we do the same command to the A2 register, it will move by just a single byte. And we can prove that just here. So because we're using a call here, this will actually affect the stack pointer. So we've copied the stack pointer to A3, and so you can see A3 is pointing to FE, but A2 is pointing to FF. Even though we've written just a single byte to both, what was originally A7 copied to A3 has gone down by 2 bytes. So, I mean, effectively, whenever we write a single byte to A7, it will actually move 2 bytes. And that's so that it stays on an even boundary for when we need to push a long or a word to the stack. That's just something odd about the A7 register that's not true of any of the other registers there.
So a very, very powerful command there. And it's not the only one. We also have pre-decrement. This is where an address register is decreased by the amount we're about to read or write, and then the read or write occurs from the address in that address register. It's effectively the opposite of the last command. So let's see that in action. So if you look here, we've read in 2 bytes, and so originally A1 was pointing at this byte here. We wanted to read in 2 bytes, so 2 was subtracted from it, and it pointed to here, and then we read in OE/OF from these 2 bytes here, and you can see that this address register is now still pointing at the first of those 2 bytes. Now, it may not be immediately apparent why this is particularly useful in the same way as post-increment was, but the main reason you're going to want to use this is the equivalent of our push command. If you know about a push command on the Z80, this is what the push command effectively does. It decreases the stack pointer, or in this case the address register, because remember address register 7 is the stack pointer, and then writes the data to that address. I mean, we were reading in this case, but pretty much all of these commands work for read and write. So this is effectively our push command. As I say again, we're going to go over stack pointers and pushing and popping and these equivalent commands in later lessons. So I'm only explaining that in case you're familiar with these other systems. If you're not familiar with it, don't worry about it at this stage. Just try and remember all of these options so that when we see them again in other coding examples, you'll have something to come back at and look at and just refresh your memory on how they worked. And you'll have these nice diagrams showing what actually happens. So, as I say, with this case, we're actually moving up by the amount that we are reading or writing, and then reading or writing from the resulting address. And of course, the address register remains at the pre-decremented state after the command occurs. So those are some pretty powerful commands, but we do have some more that are quite interesting as well. So the first one of these is address register indirect with 16-bit displacement. Sounds confusing, but it's not too bad. As in the same way as before, we're using the address in A1, but we are then adding a fixed value to it. So in this case, we're going to read in from address register A1 plus 2, and we're going to read in a single byte from the destination. Now, in our example, A1 is FF0100, and so we're then adding this 2 here that was shown with the comma before it. So we're actually going to read the value in from FF0102, and let's actually see that in example and see it work. So here you can see we are loading in from FF100 plus 2, and we are loading in effectively F2 from here because this is 2 across from FF100, and there we go. So that's all that does. Now these can be very big values indeed. We could put in 1002 if we wanted, and that will work just fine. Obviously the value is 0 because we've got no data there, but it's capable of very large numbers. Now, if you're familiar with the Z80, this is kind of the equivalent of your IX plus command. You could do IX plus 3 on the Z80. Well, on the 68000, you do 2, A1, and that would be your equivalent. One thing I do want to point out to you, if you're looking at other tutorials, especially old documentation, a lot of these commands had their structure changed. I'm using the new structure definitions, so you will see things like 5, A0 in brackets, but the old definitions would have used 5 open brackets A0 close brackets. They changed the definitions, so I'm using the newer ones. That's what Vasm uses. But if you're looking at some very old Amiga books or Atari ST books, you'll frequently see this definition here. So don't be terrified by it, don't be scared by it. All of the conversions are shown here. They didn't change things very much. They just basically changed the fixed offset from outside the brackets to inside the brackets. So hopefully not too much to worry about there, but a little bit of a pain, but I'm afraid there's nothing we can do about it. It's essentially all the modern stuff you see is going to use this new notation that I'm using here. If you've got your old books, they're going to use the old notation, which frustrating, but that's the way it is. Now that might seem fairly impressive, but there's actually much more advanced addressing modes that the 68000 processor can use. What we're able to do is we're able to use an address register, a numerical offset, and also a data register combined together to make an address, and then read from that address, or of course write to that address as the result. So we're able to use an address register, a varying data register, which we can of course change over iterations and looping, and we can have a fixed offset as well, all combined together. And so let's see that in action. So what we're going to do here is we're going to use the address register A1 plus D1 plus 2, and let's execute that. So here you can see our address register was FF0100 as usual, D1 was 1, and our offset was 2. So effectively we are now offsetting 3 from FF0100. So here's FF0100, 1, 2, 3, and that's what we've loaded in here. So we're able to do this, and it's quite of course complex, and what we could do is we could now do add.l #1, D1, and then do the same command again. And if we execute this, of course we've loaded in from 2 consecutive locations. So of course we could do a loop around this, and of course this allows us to have a fixed source address and just use the data register to change the offset that we're reading from. And so this is handy if we want to do things where we're using a bank of memory that A1 points to, but we need to work on various positions within that bank over different iterations. So a very powerful command there. Now, one thing to notice is that there isn't a command that doesn't use that offset, but we can put an offset of 0 if we want. And Vasm will actually assemble without it, even though technically there isn't a command of that nature on the 68000. But as I say, the theory is that we can actually have a fixed and a variable offset to our address register and use the combination of that result for our final reading in. As you can see here, 2 plus D1 equals FF0103, and that's where we ended up reading from here. Of course, this doesn't change the data register or the address register. So that's one of the most powerful commands on the 68000, but it's not the only command. There are a couple of other quite interesting ones. So next we're going to look at some that relate to the program counter. Well, what's the program counter? Well, the program counter is a register inside of the system. As our program executes, the CPU needs to know what byte of memory that we are currently executing, where the command is. And because of the way 68000 works flexibly with memory, and we never quite know where our program is actually running in memory, being able to do things relative to the current running command gives us a lot of flexibility if our program code is relocated to a different bank of memory all of a sudden. Because of course with the 68000 operating systems, we don't know where our program is going to load, but we do know that the 100th byte in our program is still the 100th byte in our program. So how can we use this? Well, let's have a look at a little example I've got here. So here we're going to use the program counter PC here, and we're going to read in a word, and we're going to do it twice. And we're going to read in from some test data I've put in. So I've just put 3 inline bytes here. Now, if we were actually going to have other code, we would want to put an even command here. What even does is it makes everything byte aligned to a even pair of bytes, because 68000 code is always at least 2 bytes. So that's something just important in case you're trying this at home. The example would have worked fine because there were no other commands, but just for safety I'm going to put it in there. Now what we are going to do is, in this first example, we're going to read in from the label PC test data. Now Vasm assembler will work out the offset that we have to put in here, but I've actually done it myself, and I can tell you it's 8 bytes. So we're going to read in the same bytes in 2 ways. One using PC test data as a label, and one using the mathematical number of bytes that are made up by these commands here. So let's just try executing that. So you can see we've loaded in hexadecimal 6869, which is these 2 bytes here. But of course, there's no reason why we just have to do that. We could just do 9 here, and we could put +1 on the end here. And if we execute this again, we can now see we're loading in 6970. So as I say, in some ways, you could have done a load effective address on this, and on systems like the Genesis, you could have actually directly addressed PC test data. But on a system where maybe the data is moving around in memory, or where you're actually copying it yourself into a different area of memory and executing it, which in some cases might be something you need to do, this allows you to use the current running address and an offset of that current running address, which is going to mean that your code can still run even if it ends up executing in a different place to when you originally compiled it. So there we go. Now this is one of these commands where I never needed this for Grime 68000, so if you don't understand what that means, really don't worry about it at this stage. It's another one to just remember in the back of your head in case one day you're stuck and you feel like there's a command you need that can do what you can't figure out how to do. This might be it. So just bear it in mind for the future. Now our last addressing mode is similar, but this uses only an 8-bit offset, and it also uses an index register. So again, we're using a data register added to the program counter, adding to an 8-bit fixed offset, and the result will be the memory address that we read from. So you can see that here, program counter, plus whatever our offset is. In this example, I've just used 2, and then we're loading in D1, and if D1 is 1, then we are effectively adding 3 in total and reading from that address. So let's try that here. So we've run our command again here. We've read in a single byte from PC test data plus D1. Now D1 is 1, and so whereas our PC test data or our 8-byte offset is pointing to 68, plus 1 means we're pointing at 69. So of course we can now do add.l #1, D1, and if we do these 2 commands again, you can see we've now read in 70. But of course, in all of these cases, we can also do negative offsets. I can do -1 here, which would actually read in one of the bytes from the previous line. So if we try this now, well, we've loaded in FF. I'm not quite sure which one of the bytes there that is, but as I say, it's actually part of the code we're using here. So in all likelihood, again, the reason we'd probably do that is if we'd moved test data further up. And of course, we now need to do skip here and even. Because we're putting our test data before our code, we need to skip over it because it's not executable. So, okay, so you can see here we've still been able to read in the byte 70 into D0 here, because even though the PC test data is now before this still works with a negative offset. So that's worked just fine. But as I said before, if I take out that even command and compile now, well, my program doesn't work. And the reason for that is that I'm no longer aligned to a 16-bit boundary. I could add an extra 00 here and it will now work again, but really we need to use the even command. Now, again, this is something I wasn't really going to cover today's lesson, but I never want to show you something that could cause you problems that I've had if I can avoid it. So again, if you don't understand the even command, it's not going to be something you're going to need to know about at this stage, and we will cover it again in a later lesson. So just again, feel free to forget it if it's too complex for you at this stage. Now, one important thing to notice about these program counter relative commands, and this is true of the last one we looked at as well, is that they can only be used for reading. Now, on the Genesis, this is ROM anyway, so it's kind of the case anyway. But I'm not talking about the computer can't do it. I'm talking about the assembler can't assemble it. Let me show you. So if we try to change this command to, instead of reading into D0, to set it to write to D0 to the program counter relative address, and now I recompile, you'll see here we've got an error that says instruction not supported on selected architecture. What this means is that the command we've tried to do here doesn't exist. So we can't write a register into a program counter relative address. We can only do it the other way around. But as I say, it's not a command you're going to need very often. Grime 68000 didn't need it at all, so it shouldn't be a big problem. So that's actually all of the addressing modes the 68000 has. In some ways, it kind of seems easier than the 6502 because the 6502 has more complex ones and things, but the 68000s are far more powerful, so you'll never find you in a situation where the 68000 can't do what you need. I hope you've enjoyed today's lesson. Please follow me if you've enjoyed it, because we're going to be delving further into the 68000 topic over the future lessons. Thanks for watching today, and goodbye.